So it's onward and upwards to 9.2. This time we are going to be constructing a confidence interval, but we don't know sigma. There's no population standard deviation given in this entire problem, which when you think about it is pretty realistic. I mean, in real life, if you don't know what mu is, then how the heck are you going to know what sigma is? And the answer is, well, you're not, right? There's a reason that they teach you that method first, and it's because you need it for 9.3, but I digress. So let's see here. We've got some data. Now I typed that data in. Oops, you can't see it, but there it is. I typed it in. Right? This is the age that babies first crawl at in weeks. There it is. Then it says, because the sample size is small, we must verify that the data comes from a population that is normally distributed and the sample does not contain any outliers. Here they are, right? Normal probability plot, box plot. What they're talking about? Well, let me show you. If you look back at the formula, it says right here, simple random sample is taken from a population with unknown mean, unknown standard deviation, blah, 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 right? The interval is exact when the population is normally distributed. It is approximately correct for non-normal populations, provided that n is large. Well, we don't have n being large, right? Look at our data set. N is small. We're only talking about 12 mothers here. So if you don't know that n is large and you don't know sigma and you don't know the distribution of this, which we don't, then you need to know that the data is approximately normal with no outliers. Otherwise, you can't make an interval. So we can make an interval, right? Yes, we can make an interval because the data set is normally distributed with no outliers, right? We have to know that with a small sample. If it's a large sample, then we don't care. Or if they tell us it's a small sample, but then they tell us somewhere that it's normal, then that's fine too. But if they don't tell you it's normal, then they got to prove to you that it's normal down here with this picture with no outliers. All right, now here's where the fun begins. We need to construct 95% confidence interval. And back here, I've got the formula. It's going to take x bar s square root of n and the t alpha over 2, which is not the same thing as z. T alpha over 2 is computed with n minus 1 degrees of freedom. See that? All right, so we got a lot of work to do. So let's start. First thing we're going to need, I'm going to need to make this bigger so I can see what the heck I'm doing is what I'm going to need. All right, we're going to need x bar, which is equal to the average. Let me make this maximized. Average of this data. There's x bar. We're going to need s. S is the standard deviation of this data. We're going to need n. N is how many of them there are. You could count yourself, right? Literally count. Or you could use the count feature, which I don't think I've ever shown to you guys before. But you can say count those many cells and it'll tell you there were 12 cells right there from A2 to A13. Crafty, huh? And we're going to need degrees of freedom. That's equal to n minus 1. There's degrees of freedom. We're going to need a confidence level, which was, I don't remember, 95. Okay, 0.95. You know what's coming, right? What's alpha then? Alpha is 1 minus that. You actually want to construct alpha for this one. So not alpha over 2. I know it's crazy. We want the area in, right, this is both tails. That's the way the t inverse function works. All right, now we want the critical t value, right? That's, let me put it this way. We want t alpha divided by 2. Okay, that's equal to t inverse, that one. The probability is 0.05. The degrees of freedom is 11, right? Enter. There it is. That's the critical t value. All right. I'll have to pause it here because I won't be able to fit in the last bits for this one. I'll see you the next time to finish this out.